We want to now talk about moments about arbitrary axes in space. And so we're going to start with the following. So we have some force F with a line of action, and there's some point of interest O, and we've got a position vector from point O to any point on the line of action that's shown by R. And we've actually computed the moment around O. So the moment around O, we know from before, was just R cross F. And if we have the moment about some point, then what we can imagine is how much of that moment points along different directions in space. So we could arbitrarily choose some direction that's denoted by the Greek letter lambda. It's just a direction they've shown. You could think of it as like another x-axis or another y-axis. It could be any line you want in space. And all we want to do is say, well, how much of MO points in the direction of lambda? Now, if you look at this, your brain should kind of immediately say, wow, if I had that angle right there, maybe theta, or alpha, whatever you want to think of it as being called, you say, well, that would really, all I would have to do is take MO times the cosine of this angle. I'm actually going to call it theta because we used alpha on a previous page. So we could say, well, in magnitude, m lambda is MO times the cosine of theta. And when you see that expression, I hope that brings back to you the formulation that we had developed for the dot product from before. So m lambda is equal to MO times cosine theta, but if you were to take the dot product of MO and a unit vector in the direction of lambda, then in magnitude, that would be the magnitude of MO, the magnitude of the unit vector, that's 1, times the cosine of the angle between them. And so you would find that all we're really doing is taking a dot product of our moment around O with a unit vector in the direction of this axis in space. So, define m lambda as a scalar. Okay, there are a couple of things that you need to do. So the first thing you need to do is find the moment around O. So you actually have to have the vector expression for the moment around O. The second step is to write a unit vector in the direction of your axis, whatever that axis is. Okay, that could be an x-axis, in which case you would use I for the unit vector. It could be a y-axis, in which case you'd use a j for the unit vector, or a z-axis, in which case you use a k. It could be some axis in the plane, like the xy plane. Either way, you just need to write a unit vector, and we've done that before. And then third, for a scalar form, just take a dot product. M on lambda is MO dotted with M. And then, step 4, and sometimes this one is optional, depends on the problem. For a vector form, you have the scalar, just aim it. So take the m lambda piece and multiply it by m. And that's all you have to do. Now please note that m lambda can be positive or negative. This is not a magnitude because a dot product could be positive or negative. If this moment, for instance, was pointed such that it was kind of, in the opposite direction back here, so that, when you projected it onto this line in space, you had a portion that was away from your m lambda piece, then you would wind up with a negative sign, okay? Because this one is pointed in the direction opposite m. So they can be plus or minus. It just depends on the problem that you're dealing with. So please understand that. And then when you aim it, you just take whatever that number was, plus or minus, and hit it with a unit vector, and that will tell you the vector expression for it. So again, this is a pretty straightforward thing to do here. It's not too difficult, but you do have to have the moment that is found through a cross product or the right-hand rule approach. You do need a unit vector in the direction of that line in space, and then the scalar form and the vector form. To kind of give you a different view on this, this is our other picture that we utilized. And we found this moment around O. We had that. It's got an x component and a y component and a z component. But again, I could think, well, how much of that force points in any other direction on a line that's passing through point O? This isn't quite like the projection of a force. With forces, it didn't matter where the force was in relation to the axis when I took a projection. Sometimes the axis would intersect the line of action for the force, but it didn't have to. It could be anywhere. For the moment, when you do the moment about an arbitrary axis, it is an absolute must that that axis must pass through the point where the moment is. If it doesn't, then you don't have the right expression. You just don't. Moments are forces and distances, so you've got to have the moment computed about a point on the line that you're interested in. Otherwise, your distance could be wrong. You wouldn't even have the right moment to start with. You'd be starting with a different moment. So you can't just do this about any arbitrary line in space. It actually has to pass through the point that you're interested in. Okay? Now, this alternative approach here, so I have MO. I could think about how much of this moment points in the direction of line OP. And that's what I've shown here. So I've really just dropped a line down that was perpendicular. So this is a 90 degree in here. And this MO on OP, and I've kind of written it this way. It's the moment around O projected onto OP. And so clearly that line passes through O. And that would be equal to MO dotted with a unit vector in the direction of line OP. And to form that unit vector, if I knew where point P was, I could easily do that with an angle or something like that. And then if you wanted the vector expression for this, MO onto OP, you could just say that it's the scalar multiplied by a unit vector that angles it. And that would be it. So just a little different approach to take to do a moment around an arbitrary axis. And this can be useful, especially if you're only interested in one component and maybe you've got a certain line in space that a bunch of unknowns pass through and you could take a moment around that axis. I kind of use it more for understanding vector work, but it does have its place. All right, so that is the moment about an arbitrary axis.